Hello everyone, welcome to iitiansgateclasses. This is lecture 14 on compiler design and this will be the last lecture. Okay? And in this lecture, we are going to start the next phase of compiler, that is intermediate code generation. Intermediate code generation, which is also known as ICG. Is also known as ICG. Okay. So what exactly is ICG? See, intermediate code is the code in the given language only. Actually, what exactly compiler does, it will convert a language one into language two. Language one is generally high level language and language two is generally low level language, which we have already studied in our previous classes. Now, this intermediate code is the code in HLL only. Code in HLL only, but it is represented in such a way that your low language code can be easily designed from this code. Okay. So this is a very important point which you have to remember. That is, intermediate code is the code in high level language only, but but conversion but conversion of it in LLL is easy. Okay. So it is nothing but a new way to represent HLL code only. Okay. Again, I am repeating. This is code in high level language only, but its conversion in low level language will be very easy. Okay. So let me jump to the next slide and I will show you the type of intermediate codes. All the video noted down. Yes. So intermediate code ICG is of two types. One is known as tree form and another is known as linear form. Tree form and linear form. Tree form is of again two types. One is known as AST and another is known as DAG. AST is abstract syntax tree. AST is abstract syntax tree. DAG is directed acyclic graph. Okay. And the linear form is again of two types. One is known as postfix, and second is tree address code, postfix and tree address code. So I think you already have studied postfix in your data structures and algorithm. For example, okay, I will take one example, okay, and from that example, I will show you all these four things. I will show you all these four with the help of one example only. So let me give you that example in the next slide. Pause the video, note it down. Okay. Yes. So let us suppose we have A plus B star A plus B plus C. Okay. So first I am showing you AST, abstract syntax tree. So what we will do, A plus B will be done first. So I will say plus AB. Then what we will do again, we have to add A plus B and then we have to add A plus B with C, na? Like this we will do and then we will multiply these two. Okay, so we will multiply these two. This is your abstract syntax tree. Okay, now let me show you DAG, that is directed acyclic graph. So how DAG will look like? So in DAG, okay, we will use each expression only once. So here you may argue that A plus B, why you are doing again and again? So in DAG, we will remove this disadvantage. So what we will say? So I will say plus A, B. So we have to show the direction. We are calling it as DAG, directed acyclic graph. Okay, so we have to show the directions. Let me show you here. This is a DAG. Okay, yes. So A plus B is over. Similarly, this A plus B is also over because of this. Now plus C you have to do. Okay, so what we will do plus C. I will say plus A plus B plus C. This is over. Okay, are you getting it? So plus, this is what A plus B plus C. So this entire thing is done. Now A plus B multiply this entire thing. So what we will do? Okay, let me give you the directions. So now I will use multiplication symbol, this and this. That is DAG or directed acyclic graph. So DAG is very important concept. Okay, many times question have been asked in many competitive exam regarding the number of nodes and number of edges in the DAG. Okay, so here what we will say for this expression, number of nodes are 6 and number of edges are 1, 2, 3, 4, 5, 6. Okay, so six nodes and 6 edges. Okay, so questions have been asked many times. Okay, now let me give you one more example of DAG. Okay, since questions are coming, so let me give you one more example. If I say A plus A plus A plus A, how many nodes and edges in DAG? So you have to remember each and every operand will be represented only once. Okay, so what I will say here, so for A plus A, we have to do this A plus A first. So I will add node A and I will add plus and say A plus A. Okay, like this. So please do not make another node A and then show A plus A because A is only one operand. So I will show like this. Now this addition is added again with the A. So I will add like this plus this and this. Now again added A. So I will add this and this. So each node, see this node represent A plus A. This node represent A plus A plus A, and this node represent this entire thing. Okay. So how many nodes and how many edges? So nodes are four. Nodes are four, and edges 1, 2, 3, 4, 5, 6. So edges are 6. 4 nodes and 6 edges. Okay, you have to remember all these things. Now, since it is a basic course, I'm not going deep into all these things. So I have just given you idea about DAG. Okay, and moreover, it is also used in code optimization. Okay, it is also used in code optimization. It is a type of intermediate code and used in code optimization. Please note it down. Okay. Yes. So DAG we have shown. Now see the previous slide, postfix and 3 address code. Postfix, I think you already know. Nah, so I should not show it, but let me just give you the idea how you will convert this into postfix. So first A plus B will be done. So we will get AB plus. Then again this will be done. So AB plus, then plus C, na? Then this, okay, and then multiplication. So this, so AB plus C plus star. I think you already know. I am not explaining it. Okay, just because you have studied in data structures and algorithms. Okay. The last is 3 address code. 3 address code is very important. I will show you that in the next slide. Please pause the video, note it down. Okay, so in this slide, I have shown you abstract syntax tree, directed acyclic graph, and postfix. Okay, now I'm jumping to next slide now. Okay, now I'm going to show you 3 address code. Okay, so 3 address code is, okay, so see, 3 address code means each and every line. What does 3 address code means? 3 address code means each and every statement must have at most 3 addresses. At most 3 addresses. Okay, that is the basic condition in 3 address code. As the name suggests, each and every statement must have at most 3 addresses. So let me take it. Okay, A plus B, A plus B plus A plus B plus C. So in this statement, how many addresses are there? 1, 2, 3, 4, and 5. Basically, these are the variables. So this is 5 addresses, but we want 3 address code. So let me show you how we will convert it. So I will say A plus B, you will done first. So T1 is equal to A plus B. Okay. And then what we will say, okay, here we have a star now. Yeah. A plus B star, A plus B plus A. Then we will do, now I will come here. Okay. So T2 is equal to A plus B. T3 is equal to T2 plus C. Are you getting it? A plus B is T2 and then plus C. Now, T3 is equal to T2 plus C. Now, T3 is this, T1 is this. So, T1 multiplied by T3. So, T4 will be equal to T1 multiplied by T3. This is the way. You may argue with me that, sir, T1 is equal to A plus B. Already we have done. Then why we are doing it again? No problem. You can skip it. Okay. I'm just showing you that how it is done. By the way, this all will be done in code optimization step. That is the next step of in compilation. Okay. So this is done in a code optimization. But no need to worry. You can show it here also. Okay. So that is the way to show. Are you getting it? So this is the 3 address code. Now the question comes, how this 3 address code will be represented in computer. Okay, so there are several ways of representation, and since it is a basic course, I will show you only 2 ways. Okay, so next question is how this code will be represented in computer. How this code will be represented in computer. Represented in computer, or you can say stored in computer. Okay, so for that we have 2 ways. First is quadruple and second is triple. Okay, let me show you that in the next slide. Please pause the video and note it down. Okay, so for explaining quadruple and triple, let me take another example. A plus B star A plus B star C. This is our code. Okay, so quadruple means 4 columns. Okay, so first will be obviously serial number, then operand, operator, then operand 1, operand 2, and then result. So what we will say? We will say, so see here. Actually, okay, so first let me show you the 3 address code here. Okay, then I will show you the quadruple. So how 3 address code will look like? I will say T1 is equal to A plus B. First we will do this A plus B. Then T2 will be equal to minus T1. Okay, why I am showing you here? You may argue, sir, we need 3 addresses, but here we have 2 addresses only. T2 is equal to minus T1. See here, I have shown you at most 3 addresses. The previous slide I have already told you. Okay, so T2 is equal to minus T1. Then what we will do? Then we will say T3 is equal to B star C. Now first B star C will be done. Yes, first this will be done. So B star C. Okay, then T4 will be equal to A plus T3. Okay, are you getting it now? T3 is equal to B star C. Then this will be added with A now. So we have done this. Okay, and then finally T2 has got what? T2 has got this minus A plus B. T4 has got this entire thing, and we want to multiply them. So what we will do? I will say T5 is equal to T2 multiplied by T4. That's it. So this is the 3 address code which we have done. Now you just represent it as it is in our table. Okay, just represent it as it is in our table. So I will write serial number 1, but I will say plus A, B, T1, serial number 2, minus T1. Okay, second operand is missing. You will say T2, serial number 3, multiply B, C. We have got T3, serial number 4, plus A, T3, T4, and serial number 5 will be star T2, T4, T5. I think you have got it. These are very simple. I have just noted down as it is in my table. Okay. This is known as quadruple because there are 4 columns. Forget about the serial number. That is obvious. These are the 4 columns. That's why it is known as quadruple. Okay. Now let me show you triple. Okay. Yes. Please note it down and I'll jump to the next slide. Or rather, I should do it here only. Okay. Just to save the time, I will do it here only because we have already done the 3 address code. So I will just represent it. So how I will represent it? I will say serial number, operand, operator. OP means operator. Operand 1, operand 2. Okay, so how I will show 1, serial number 1 is plus AB, serial number 2 is minus 1, serial number 3 is star BC, serial number 4 is plus A3 and serial number 5 is star 2 4. So you can imagine that this one is storing the result. Okay. So for result, we were having a temporary variable in quadruple, but in triple, this column is missing. So you can imagine one has got this. Okay. So A plus B. Actually, we have a pointer here. Serial number one means pointer to this expression. Okay. So A plus B. So roughly, you can imagine A plus B is stored in one. Okay. So now minus one means what? This will minus sign with this and so on. I think you have got it. Okay. 3 is star BC. So A and 3 are added. Okay. So star BC, matlab B multiplied by C and plus A. This thing will be done. And so on. I think you have got it. Okay. This is triple. Okay. So the basic disadvantage of triple is you have to execute this statement again and again. So when I say minus 1, then you will come to 1 and you will execute it again. When I say 3, so you will come to 3 and you will execute it. 2 means what? You will come to 2 and execute it. So for 2, I will come here and execute this. So for here 1, so I will execute 1 again. Okay, so again and again we have to do many things, but the only thing is space is saved. Here we have 3 column and here we have 4 column. Okay, so this is known as triple and this is known as quadruple. Okay, so I hope I have made the point clear to everybody. Please pause the video and note it down and I will jump to the next slide now. Okay. Yes. So that's it. This is all about code optimization. Now we will start, for intermediate code generation over. Now we will start code optimization techniques. Okay. So intermediate code generation is over. Now we will start code optimization techniques. So code optimization, let me tell you, this is an optional step in compiler design. So it may or may not be used. Okay. But in some compiler, this is one of the major steps, and those compilers are known as optimizing compilers. Okay. Optimizing compilers are those compilers in which code optimization is one of the major steps. Okay. Yes. So now let me show you code optimization techniques. So there are several techniques. Okay. Let me label them one by one. So first is loop invariant, or let me say loop optimization. Loop optimization. For loop optimization, we have three kinds of loop optimization. First is loop invariant. Loop invariant. Second is loop unrolling. Loop unrolling. And third is loop jamming. Loop jamming or loop combining. Okay. Yes. Second optimization technique is constant propagation. Constant propagation. Third technique is redundancy elimination. Redundancy elimination. Okay. Fourth technique is strength reduction. And the fifth technique is algebraic simplification. Algebraic simplification. Okay. Yes, so let me show you one by one these techniques. So first is loop optimization. Please pause the video and note it down. I'm jumping to next slide. Yes. So first is loop optimization. Okay, so we have three types of loop optimization. I'm not going to write them again and again. First is loop invariant. So let me show you that. Okay. So first is loop invariant. Loop invariant. What is loop invariant? For example, if I say for I is equal to 1, I less than equal to 1000, I plus plus, and I am saying A is equal to B star C star I. Okay, so now we are multiplying B and C again and again. This is the body of the loop. That's it. Okay, there is nothing more than that in the body of the loop. We are multiplying B and C again and again, and we are multiplying it by I. No doubt, I is changing again and again, and we are multiplying it by I. No problem. But why we are doing multiplication of B and C again and again? We can keep it outside also. So we can keep this B star C outside the loop. Actually, this is loop invariant. Okay, this is loop invariant because it is not changing. I will keep it outside the loop and I will say T is equal to B star C, and here in place of B star C I will write, so in place of this statement I will write A is equal to T star I. So directly indirectly we have saved 1000 multiplication. We have saved 1000 multiplication. I hope you have got my point. Okay, so keep the loop invariant outside the loop. Okay, otherwise it will just keep on wasting CPU cycles. Okay, so I hope I have made the point clear. Please pause the video, note it down, and I will jump to the next slide now. Yes. So the next is loop unrolling. See the slide. Loop invariant is over. Now the next is loop unrolling. Let me show you the second category of loop optimization, that is loop unrolling. What is loop unrolling? Let me give you one example. If I say for I is equal to 0, or okay, let me take it. So let me take it. I is equal to 1, I less than equal to 1000, I plus plus, and I am saying x of I is equal to I. So directly indirectly I want to say array. We have array. So x of 1 will be 1, x of 2 will be 2, x of 3 will be 3, and so on. We want to do this thing. So obviously loop will be executed 1000 times. So I can unroll it. Unroll means I can say, in place of this, I can say for I is equal to 1, I less than equal to 500, I plus plus, and here I will say xi is equal to I plus plus, xi is equal to I. Okay, so now please try to see yourself. These two codes are exactly same, exactly equivalent. The only advantage here is we have to run the loop 500 times, but here we have to run the loop 1000 times. Okay. Okay, so I have done a small mistake here. I should write here 1000. Sorry for that. Okay. So loop will again 1000. No doubt you will say 1 to 1000. No. Actually, it is not going from 1 to 1000. I plus plus will be done 2 times. So obviously loop will run 500 times. Okay. So again, I'm repeating, no doubt you may argue with me that loop is running 1000 times, but actually it is not running 1000 times. No doubt I is going from 1 to 1000, but with increment of 2 each time. Okay. So firstly, I will be 1 here. So x1 will be 1, then I plus plus. It will be 2, then x2 will be 2, and then again I plus plus. Then x3 will be 3, and so on. So obviously, body of the loop will be executed 500 times only, and here 1000 times. Okay, so obviously this is much better code than this. So you can do like this. This is loop unrolling. Now I'm jumping to next slide to show you the next optimization. That is loop jamming. Loop jamming or combining. Loop jamming or loop combining. This is the third optimization. You can see the slide. Okay, loop jamming or loop combining. This is our third optimization. Yes, what is this? So let me say it is just opposite kind of thing. Okay, so I will say for I is equal to 1, I less than equal to 1000, I plus plus, xi is equal to I. Again I am writing for j is equal to 1, j less than equal to 1000, j plus plus, yj is equal to j. So directly indirectly, what we are doing, we have say 1000 element array, and we are initializing each element with the number. That means x1 with 1, x2 with 2, and so on. Similarly here also, y1 to 1, y2 to 2, and so on. So same is the case now. Okay. So same thing we are doing. So why you are using two loops? We can do it with one loop also. Okay, how? Let me show you. So the better code will be, I can replace this code by this. For I is equal to 1, I less than equal to 1000, I plus plus, xi is equal to I, yi is equal to I. So simple. Please try to see yourself. Both these codes will give you same result. Okay. So that is the big advantage here. Okay. So now this is body of the for loop. Both will be done. Okay. So obviously this is much better code than this, because see, while running loop, I think you have studied in computer architecture. We have to initialize the loop. We have to initialize registers and so on. That will take a lot of time. Okay. Okay. So a lot of resources will be saved when in place of two loops, we are using one loop. Okay. So please note it down, and I will jump to the next slide. Okay. So now we will jump to constant propagation. That is the next code optimization technique. What is constant propagation? Constant propagation. For example, if we have written like this 2 plus 3 plus 4 plus 5 plus y, if we have written like this in the code, so why you are writing like this? Please do small amount of work. It will be 14 plus y, na? 2 plus 3 is 5, 5 plus 5 is 10, 10 plus 4 is 14. So in place of this, you should write this. Okay, so obviously lot of time will be saved. Okay, so ALU, in ALU adder circuit will be activated, and then 2 plus 3 will be done, then 4, then 5, and so on. So why you want to waste time in all these things? And this is a very simple calculation. You can do yourself also. So please try to save the time here. So in place of writing constant multiple time, you just calculate the value of constant and you just add with the variable. That is constant propagation. Okay. Yes, I'm jumping to next slide now. Next is redundancy elimination. See the slide? Yes. Now we will jump to redundancy elimination. Redundancy elimination. Okay. Let me give you a small example. A is equal to B star C. Y is equal to B plus 2 plus C plus 3. Z is equal to C plus 1 plus B. Okay, this is the code. So here we are doing redundant things again and again. Can you tell me what are the redundant things? See here, we have already calculated A is equal to B plus C. Here we are adding B plus C again. So we can replace it by A na, because A is already having result of B plus C. Similarly, here also B plus C is done. So why you are adding them again and again when you have already calculated and stored the result in A? So in place of this, better code will be, we'll write A is equal to B plus C, Y is equal to 5 plus A, Z is equal to 1 plus. I have done constant folding also, 2 plus 3. Constant propagation or constant folding, one and the same thing. Okay. So constant propagation I have done here. So 2 plus 3, I have calculated 5 plus 8. This is the much better optimized code. Okay. And for redundancy elimination, which data structure will be used? This question has been asked. So I think you have got it. Yes. That directed acyclic graph will be used for redundancy elimination purposes. Okay. So I think you have got it. So okay. So for this, we will write it like this. So B, C, both are added now. So let me label it as A. Now Y is equal to 5. Let me write it like this: 5 plus B plus C. B plus C we have already done. So I will write plus 5. This will be your Y. And what will be our Z? 1 plus C. Okay, so 1 plus C plus B. So B plus C is already A. So Z will be what? A plus 1. Okay, so this will be our Z. Okay, so that is done with the help of that. I'm not going into details, of course, because this is a basic course. So I've just given you idea Redundancy elimination is done with the help of DAG, that is directed acyclic graph. That's it. Okay. This question has been asked many times. That's why I have told you. So redundancy elimination code optimization technique. Which data structure is used? DAG, directed acyclic graph. And I have already told you in code optimization. See, I have told you previous slides, a few slides back, that DAG is used in code optimization. So I have shown you here. DAG is actually what? Intermediate code generation type. Okay, this was DAG, and it is used in code optimization also. How it is used, I have told you. Okay. Next is strength reduction. See the slide. Next is strength reduction. What is strength reduction or reduction in strength? We can use any word. One and the same thing, strength reduction or reduction in strength. Okay, what is this? So, for example, I want to multiply x by 2. In place of this, I can use left shift operator, x2. Okay, I think you already know about left shift and right shift. You have studied in computer architecture, so I'm using that operation. Multiplied by 2 can be replaced by this, sorry, 1. Sorry for that. Multiplied by 2, so I will do 1 shift. X multiplied by 4 can be done by x left shift 2. Similarly, x divided by 2 can be done by x right shift 1. X divided by 4 can be done by right shift 2. Okay. So what exactly is done here? So x multiplied by 2 power n. That means x left shift n. This n here. And x divided by 2 power n is x right shift n. This n is here. Okay. So for example, see here, 4 is what? 2 power 2 na? So 2 is here. Similarly, x by 8. So this is nothing but x by 2 power 3. So we will do 3 right shifts. That's it. Okay. So strength reduction means what? So what is will be the basic advantage here? Multiplier circuit of ALU will be activated here, and then we will do multiplication. Here there is no need of ALU. We are just shifting the bits. That's it. Okay. So strength reduction means replacing. I will show you I will show you the definition of it. Please try to follow it. This has been asked many times in UGC-NET and other competitive exam. Strength reduction means replacing costly operation with less costlier one. Replacing costly operation with less costlier one. This is a costly operation. Obviously, it will take a lot of time, and I have replaced it with less costlier one. Okay. Yes. So I hope I have made the point clear to all of you. Please pause the video, note it down, and I will jump to the next slide. So let me show you. Last is algebraic simplification. Let me show you that also. Algebraic simplification. What exactly is algebraic simplification? See, sometimes by mistake we write like this. Okay, we should not do like this. This is algebraic simplification. Okay, this must not be done. Obviously, both are same, na? So why you are activating the adder circuit of ALU and then you will add it, or why you are activating multiplier circuit here and you are multiplying them and so on. So we should avoid all these things. Okay, this is algebraic simplification. As soon as compiler see these lines, it will simply delete all these lines. Okay, saying that these are not useful lines. So I hope I have made the point clear to everybody. So that's it. So thank you all of you. Here our compiler design is completed. Thank you all of you. Thank you for watching.